Good morning, good afternoon, good evening, wherever you may be in this part of the world. Welcome to another session of my presentation series, and this time my got very interesting topic, and the title is Understanding and How to Read a Single Line Diagram for a 13.8 kV switchgear all the way up to 480 volts level switchgear. My good name is John Kweku Amotu, and I've been a professional electrical engineer for the past 31 years, and I'm based in the United States of America. Okay, now let's talk about some important logistics over here. Um, if you like my YouTube, right? Basically, if you like this presentation that I'm making, don't forget to subscribe and don't forget to select the like button in YouTube. And also below that is my YouTube channel, and that has a lot of interesting presentations over there, and that is very important to you as a young engineer that is developing your career, and also as a mid-career engineer, discipline engineer, and also as an experienced engineer and that wants to refresh. It's very important. Even if you're an experienced engineer, sometimes you need to have a refresher. So we have a yearly refresher courses that we take. So this is very important. If you go to the YouTube channel, there's tons of learning presentations out there that can help you to refresh your knowledge on a yearly basis. Okay. Okay. So for a one-line diagram, right? It's one of the important key items that you see on a single line diagram. It's a legend. Okay. So basically, the legend that you see is usually on the right-hand side of the single line diagram. That tells you some of the descriptions and what symbols basically has the symbols and descriptions, the meaning of the symbols. Okay, so as you can see over here, you have the symbols, right? What it means is a draw out vacuum circuit breaker, right? And usually it is on medium voltage switchgear level. So once you're able to uh, if you're an experienced engineer that basically you've been drawing one line diagram or you are familiar with the one line diagram, then you don't need to review the legend, basically, to find out what they mean. You automatically you know what what symbols those means, But as you're learning, it's very important. Okay, so you take a look at it on the right hand side. That's where the legends. Uh, so this one shows that you see the arrows over here, right? The arrows tells you that they are the draw type. It means that you can easily remove the circuit breaker if you want to do testing or maintenance on it. So that's what those symbols mean, right? Okay. Then this is a symbol for a transformer. Okay. Then if you have a disconnect link, and it's fused, especially motor control centers, medium voltage motor control centers are for basically motor control for motors, right? You'll see this symbol over there. So this is the rating of the fuse, and this is the disconnector link that is fused. Okay. Then on the low voltage side, you'll see a symbol like that, 480 volts level. This is a power circuit breaker. Okay, so and this arrow up and down over here that tells you that it is withdrawable. It's a draw type. It means that you can remove it basically, in a de-energized state and to test it or perform maintenance on it. Okay, so another symbol that you see, it's a cable bus, right? Okay, so this is a symbol of a cable bus. Then a splice cable, that is a two cables that have been joined together. Sometimes it becomes necessary to splice based on the run of the cable, or sometimes if a fault occurs and you have to repair the fault. Okay, so now let's take a look at the full scale single line diagram all the way from 13.8 kV. 13.8 kV, it's basically the medium voltage level, right? Okay, so as you can see over here, right? you have a feeder that comes in here, right? Okay, so you can have different medium voltage 13.8 kV level switchgears that are in the facility, right? That are basically interconnected with each other. So this can come from another medium voltage switchgear that is located in the same facility, right? So these medium voltage switchgears are interconnected and cascaded all together, right? So you have a feed, let's say 13.8 kV from a medium voltage switchgear. This is the circuit breaker that comes in here, right? Then from another medium voltage switchgear. Remember, I made mention that redundancy is very important, right? 13.8 kV switchgear, 13.8 switchgear. Uh, okay, so redundancy is very important. So that is why we power this medium voltage switchgear from different sources, so that if you lose one source, you should be able to provide reliable power to the switchgear from the other source. I mean, think about it. There's no way you can have um, losing power sources from or to sources. Okay, definitely, there's the possibility that, you can have one out of the two sources going out. So when that happens and that it becomes possible to close the tiebreaker, and basically if you lose the source, right? Then you should be able to power this switch gear from the source and just close the tiebreaker, right? So redundancy is implemented and is very important in the design of power system networks. Okay, and also added, reliability and security for the power systems network. Okay, so you have a source that comes in here. So this is 13.8 kV switch gear. This is bus one. This is bus two, right? And in between, you have a tiebreaker, right? That is normally open. Okay. Okay. So basically, you have two sources that is providing power for each bus in certain configuration, right? Like I said, it depends on the design, right? Like sometimes you can have the tiebreaker closed, and when the tiebreaker is closed, what happens? It means that the available short circuit current can be very high. So so what happens is sometimes if they do the system studies and they do the analysis and they find out the available short circuit analysis, it's very high. What they do, they put in it's a fault current limiter, to limit the short circuit if there should be a fault, right? So these are basically the design stage, planning part of the design. They do all the system studies, they do all the scenarios and simulate all the scenarios to determine the best, parameters to be able to design the and part of the equipment selection level and the parameters selections for the bus. Okay, so this bus, for instance, should have a continuous current, nominal current, right? And short circuit capability. And the short circuit capability, you should have a symmetrical and asymmetrical. Asymmetrical is actually the highest peak short circuit current, right? That is more of a mechanical operation of the components of the switchgear, right? To be able to withstand, and that usually happens during the first quarter cycle of the fault, right? Where you have the asymmetrical fault contribution due to the X over R ratio, especially if you have a motor rotating machines that contribute, or you have an emergency diesel generator that is running, and basically they contribute to the fault. Yeah, so that itself helps. That is the peak part of the fault, and basically that determines the asymmetrical short circuit capability, based on the DC offset, right? Okay, so this happens during the first quarter cycle of the fault, right? Okay, so the fault basically peaks, and basically it basically tapers, right? Okay, so there's a DC offset, right? Value uh, based on the X over R ratio up to the point of the fault. Okay, so over here you have the incomer breaker, right? And over here you have an incomer. Definitely, you need an incoming breaker. So there's a section on the switchgear, dedicated cubicle, that you have the incomer breaker there. Then there's also a dedicated cubicle, right, for the tie breaker, right? Then the rest are all cubicles on the switchgear lineup, right? They call it a switchgear lineup. Okay, so you have bus one over here, right? Then bus two over here, okay, or bus A, bus B. Okay, so you have cubicles with dedicated breakers to feeders, right here, as you can see over here, right? Then there's also a dedicated breaker for the tiebreaker, and it could be, normally open or normally closed. Like I said, we have different scenarios, and it all depends on the customers' wants. And basically, if the tiebreaker is closed, then basically I explained to you the drawback that is associated and what you need to engineer to be able to limit the short circuit current. Because if once you close the tiebreaker in uh, normal operation, then basically your short circuit currents are going to be available. Short circuit currents are going to be very high, and you need to have a current limiting limiter to be able to limit the amount of short circuit current, so that your switchgear design wouldn't be so expensive and equipment wouldn't be so expensive. Okay, so these are all dedicated cubicles on the switchgear lineup, dedicated cubicle, and you know to be able to accommodate for future expansion of the switchgear. Sometimes there's something they call equipped space. You need to have spare cubicles, okay, so that in the future it helps you to be able to add you know, uh, another feeder, right, to power, another load, right? Okay, and before you do that, you also have to do system studies, yeah, to make sure that the load that you are adding wouldn't exceed the rating of the feeder and also the bus rating. Very, very important. Okay, so this is all part of facility modification projects that requires system studies. Right. Then we can also have an equipped space, right? Okay, so where basically that cubicle will be empty, but we'll just have stops for you to add the breaker. Okay, so as you can see, you have feeders over here, right? That comes to this transformers, right? Okay, so the goal of this transformer is to step down the voltage from a 13.8 kV level to 480 volts, right? Okay, so this for you, because you need motor control centers, right? Especially, if you have an industrial facility, right? You have a generation facility, and a commercial facility that you require 480 volts, right? Okay, so you need a dedicated transformers that are installed in various facilities, various you know uh, miniature substations within the facility to be able to step down the voltage from 13.8 kV to 480 volts, right? Okay, so as you can see over here, I have a feeder that comes from a cubicle through a dedicated breaker that comes to this transformer that steps down, and another feeder that comes here, another feeder that comes in 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 here, right? So the goal is we are trying to achieve a voltage level that is appropriate for a motor control center. As you know, a lot of the motor control centers, 480 volts, right, based on ANSI standard, right. In the IEC, they also have different voltages, 440 volts, 415 volts, and etc. But based on American standards, we have a 480 volts level for motor control centers. Okay, so once I step down the voltage from 30.8 kV to 480 volts, right? Okay, I'm able to achieve 480 volts motor control center, right? Okay, so for the 480 volts motor control center, it's the same philosophy, just like the medium voltage switchgear, right? Okay, so I have a bus 1, bus 2, right? Or bus A, bus B, right? Okay, and I have an incomer breaker, right? And same philosophy, right? Okay, so we have when we are designing, redundancy is and availability, reliability is very important, as part of the design. So that is why we have dedicated sources. As you can see over here, right? We have a feed from different sources, right? You can see this feed is coming from this bus, then another feed is coming from this other bus. So that if this bus should be faulted, then I can have a reliable bus feed that is coming from here. Then all I need to do is basically close the tiebreaker, right? So, and there are protective schemes that are in place to be able to detect the loss of voltage from one bus, and basically it has a um, um, relay, basically, device 25 and some timers, right? That basically determines the level of the voltage and the delay for it to be operate an automatic transfer scheme switch to be able to close the tiebreaker. Okay, so within this 480 volts, similarly, you have basically different breakers. Okay, so like I indicated, even then for this 480 volts, you can basically feed it to multiples of motor control centers. Let's say, even hundreds of motor control centers, right? Okay, so basically you have a feeder that from here is going to this motor control center, right? As you can see over here, that basically feeds a lot of motors. So these are all motor loads, right? That is why they call it motor control centers, right? Or motor loads, motor loads, motor loads. Then you have another feed over here, right? That goes to this motor loads, right? Okay, and matter of fact, this also can be another level for you to feed other motor control centers, right? Okay, so you can have a feed that is coming from here to a typical, so within this facility, that's how basically we develop this 480 volt voltage and motor control centers. Okay, so as you can see over here, these are all motor loads that these motor control center basically powers, right? Okay. Okay, so now let's take a look at um, a typical example of how this 30.8 kV level uh, switchgear looks like. Okay, so like I indicated, right? Okay, this is a feed that is coming from a dedicated source, right? Let's say it could be, let's say, coming from another medium voltage switch here, 13.8 kV medium voltage switchgear, right? With a breaker, then it comes from here. Or it could come from a transformer that steps the voltage down, let's say from 69 kV or 115 kV to 13.8 kV level before it comes in here. Okay. So when it comes in here, right, this is an incomer breaker, right? Okay, so this is a 1200 3200 amps breaker, right? That is for this switchgear. So this switchgear is a 2.4 kV level, right? Switchgear, and that is also a medium voltage switchgear. And the continuous ampere is 1500, and the short circuit capability is 50 kilo amps, and it's a 3-phase and 60 hertz, right? Okay, so these are the parameters of the bus. And basically, this is determined and part of initially as part of the system planning process, where um, system studies are performed, load flow, short circuit studies, right? So based on that, then based on the simulation, they are supposed to do the equipment selection parameters, right? And it should be about 15% above what their system studies is providing them. Okay, so then you have a tiebreaker, right? Okay, so the tiebreaker usually is normally open, but like I indicated, you can also have a tiebreaker that is closed, and usually I indicated, the drawbacks that is associated with it. It means that if the tiebreaker is closed, you can have a very high short circuit current flow during fault condition or during motor starting conditions. So basically, you need um, a fault current limiter. Usually you see that they have a fault current limiter on the low voltage side of the transformer if it is fed from a transformer, or you can have a fault current limiter in the tiebreaker, very, in series with the tiebreaker to limit the amount of fault current when they are starting because of the inrush, due to motor starting, which basically results in high flow of inrush amount of currents to help the motor starts. Okay, so this is the breaker, right? This is the breaker basically, as you can see, and I indicated from, the legends, right? The legendary, symbols, right? Okay, I indicated that, this is a withdrawable breaker. You see, this is, they call it the breaker stops, right? Okay, so these are the breaker stops, basically that shows you that it's a draw breaker rated at 3200 amps. So this is the continuous rating of the breaker, right? On the other side, like similarly, like I told you that you have a redundancy that has been put into this design. Okay, so this probably is fed from another 13.8 kV switchgear with, dedicated breaker from somewhere. Okay, and basically this is fed into. So this breaker that you see over here is part of this switchgear. There's an incomer cubicle main breaker. They call it main breaker or incomer breaker. Depending on wherever you sometimes in the oil and gas they call it the incomer breaker. Okay, so this is the rating of the breaker, 3200 amps, right? And similarly, I told you that this tabs you see it shows that it is a withdrawable cable, right? Okay, so and you can have a different feeds, right? You can have a cable bus, you can have a cable feed, uh, different configurations, so but this one we have a cable bus that is feeding this switch gear. Okay, so this is bus 1 and bus 2, or bus A, bus B, right? Okay, so similarly, I told you that redundancy is very important and reliability is very important. So that if one bus should be faulted due to a fault condition, right? I should be able to reliably provide electrical power, to feed to all these loads, right? Okay, so if this bus should be faulted, I should be able to close the tiebreaker, or during maintenance, or another scenario is maintenance, right? Yeah, if I have to do maintenance on this bus, then I should be able to isolate this bus and close the tiebreaker and be able to feed this all these loads from this source, and vice versa. If I have to do maintenance on this bus, or if there's a fault on this bus, I should be able to isolate this bus and be able to feed and close the tiebreaker and feed from this side. Okay, so this shows the rating of the breakers, right? Okay, so 1200 amp frame. Okay, so the frame of the breaker, that is the capability, right? Of the breaker, that is 1200 amps. Okay, so and 1200 AT means that it's a triple logic. It has That is the rating of the trip logic in the breaker. Some of the breakers have trip logic schemes that basically helps to basically do set the protection schemes. So but the trip logics have a long time pickup, long time delay. They also call them solid state tripping uh, pickups. Then short time pickup, short time delay, then instantaneous pickup. Okay, so this is what they call the solid state trip logic scheme. So that helps you to uh, develop your settings for protection of So as you can see, over here, right? Okay, so this is basically an equipped space, right? Okay, so and this is a spare. That is, it has a cubicle that has a breaker there already dedicated, that can be utilized in the future, right? Okay, so all these are part of the design stage. You need to think about the future, how and plan for it. It means that if you have to add a load in the future, already have a dedicated breaker over there. I mean, then you don't have to think about going to buy a breaker and put it in there. You already have a breaker in there, and you have an equipped space where you can buy a breaker and put it in there. Or if you have a spare breaker in your spare inventory, then you can basically go and bring that breaker and basically install it in there. Okay. So this is also another feed that goes to motor, right? They're rated at this horsepower, right? This is another feed that goes to a 300 horsepower motor, and this is another feed, right? This is another feed, as you can see over here, and this is an equipped space, right? Okay, so this is an example of basically how the medium voltage, for the medium voltage voltage levels, we have 2.4 kV, we have 6.9 kV, and 13.8 kV, as a part of our ANSI standard. And that is what you see typically in North America. Okay, so now let's take a look at this 13.8 kV level single line diagram, right? Okay, so like I indicated to you, redundancy is very important, and reliability is very important. As you can see, you have a feed that comes from here, and that can be fed from another medium voltage switchgear, or it can come directly from a step down transformer that steps the voltage, let's say 115 kV to 13.8 kV level, right? Then it comes in here, or it can come from a medium voltage switchgear 13.8 kV with a feeder breaker, then it can come in here. Okay, similarly, so this is bus 1, bus 2, bus A, bus B, right? Okay, and all the reason why you have two buses is based on redundancy, right? Okay, very, very important, and based on the load that they build during the design stage. Okay, so these are what you see over here is the rating of the bus, right? Okay, so you can see the nominal voltage rating for the bus is 13.8 kV, right? And the continuous current rating is 1200. And the symmetrical short circuit rating is 31.5 kiloamps for 3 seconds. And that is the short time symmetrical rating. So for the short time symmetrical rating, you can have a 31.5 kiloamps, either 1 second or 3 seconds. So, right. So that is the wish time. And the asymmetrical rating is higher than that, because you have to factor the asymmetric factor into it based on the DC offset and X over R ratio. Okay, so this is a 3-phase, of course, and 60 hertz, 3-wire, and a copper bus, right? Okay, so this is the tiebreaker, and normally open, right? The only time you have to close the tiebreaker is, let's say you want to perform maintenance on one bus, right? Or there's a fault on one bus and you need to provide power to all these loads, right? From either source. Okay, so similarly, this is another feed from here. So this is the incomer or the main breaker, right? And that is in a dedicated cubicle. Usually, the main breaker, you see it as the first cubicle, right? That is in the switchgear lineup. Okay, and the tiebreaker is usually in the middle. Okay, so these are the feeds that you can see over here, and let's talk about this, right? Okay, so this is if I need a 480 volts voltage level, right? I need to step down the voltage, and this is basically the feed. Okay, so this basically tells you the cable feed, right? And the size of the conductors, right? The phase conductors and the ground conductors. As you can see over here, it requires a 3 core conductors, right? 3 cores. Okay, so one conductor has 3 cores for 3 phase, right? Okay, by 2 of them. Okay, we are utilizing 2 of them. And the ground conductor, the size of the ground conductor. So basically, it's telling you that this is the cable number, right? PC9197. So that's the name of the identification of the cable, and this is the mix composition of the cable. All right. Then before it comes to this step down transformer, right? This step down transformer has a delta wound on the primary side, and on the low voltage side is a Y resistive ground transformer, right? Okay, so, and this is the rating of the transformer. It's 13.8 kV, 4.16 kV, or 2.4 kV, right? Okay, so, and it has two ratings. That is 10 MVA, 12.5 MVA. That is the 10 MVA being the Onan rating. That is operating with a natural convection and also natural flow of air. And 12.5 is the ONAF rating, that is operating with forced air when the fans are on. That is when the transformer picks up additional load. Then that is when, So this symbol basically shows you the Y side, the low voltage side is a resistive, resistance grounded, right? Okay, and basically to limit the fault current to a level. And the fault current level limiting is 400 amps, as you can see over here, for a period of 10 seconds, right? Okay, so that is basically IT, basically the current and the time basically that corresponds to heating. Okay, so that is how the sizing of this resistance it's and also this is the vector configuration of this transformer is DYN1. So that shows that the high voltage side, the 13.8 kV side, is wound in delta configuration, and the low voltage side, it's wound in a Y configuration. Okay, so I'm trying to, basically, this is a feed that goes to trying to achieve a 4.16 kV or 2.4 kV level of medium voltage switchgear. Okay, so similarly, this is another feed, right? Redundancy is very important. Okay, so basically it goes to in here, and similarly, I'm trying to achieve another medium voltage switchgear at a voltage level of 4.16 and 2.4 kV. Okay, so I have to step the voltage down from 30.8 kV. Okay, so similarly, I have a step down transformer that steps the voltage down from 30.8 kV to either 4.16 kV or 2.4 kV. And basically, the transformer has an Onan rating of 10 MVA and an ONAF rating of 12.5 MVA, right? Okay, and basically, the low voltage side, it's Y resistance grounded, and this is very important, especially for industrial facilities, right? Okay, where basically you want continuous operation, to limit the damage to the equipment, basically, so the amount of fault current that will allow the ground fault currents to basically, identify the fault and basically, trip the equipment is 400 amps, and the maximum duration is 10 seconds, right? This is how much the resistor can withstand without basically any failure, right? Okay. So similarly, it's another feed that goes to another step down transformer, right? Okay. And but this time we are stepping it down from 13.8 kV to 480 volts, right? We are trying to achieve, basically achieve a motor control center at a 480 volts. Okay, so this is how we are able to synthesize different voltage levels at different medium voltage levels, 13.8 kV to 4.16 kV to 2.4 kV. And matter of fact, we can even go from 13.8 kV to 6.9 kV. And also, we can go to the low voltage side of 480 volts utilizing this feed, where you have a transformer that steps down. And as you can see over here, this is solidly grounded, right? Comparable to the medium voltage, right? So the low voltage side, the white side, is solidly grounded, right? And you can see you have cable bars with this rating, short circuit rating of 85 kiloamps, and also continuous rating of 4000 amps. This is basically the size of the cable, right? Okay, so you have a three conductor, right? And basically this is the size, and the size of the ground conductor. And so you have one three conductor cable that is in that bus, right? Basically, there is an enclosure, and, cables laid phase A, phase B, phase C, and basically there's a dividing barrier. Sometimes you can have a dividing barrier in between each phase. So it goes to this step down transformer with a voltage step down 13.8 kV to 0.48 kV. Then this is the rating of the transformer, 2.5 Onan rating. That is natural convection, natural flow of air without any fans, and ONAF of 3.125 MVA, right? And this is the vector configuration, dy and 1. So that shows that the high voltage side is wound in the delta wound. As you can see over here, the low voltage side is wound in a Y, solidly grounded. And the 1 means that the high voltage side is leading the low voltage side by 30 degrees based on the clock system. Okay, so now let's talk about this single line diagram. So this is a 2.4 kV. Okay, so basically I've been able to this is a feed that is coming from the other diagram, right? Okay, so from a medium voltage 13.8 kV switchgear, right? Okay, so I'm feeding this one. This is the identification for the cable. Okay, so the cable, and this is the size of the cable, right? So you have two three conductor cable, and this is the size of the phase conductor, and the ground conductor is this. So the phase conductor is 185 mm squared, and the ground conductor is 95 mm squared. Okay, so it comes to this step down transformer that steps the voltage down from 13.8 kV to 4.16 kV or 2.4 kV, and has this on and on off rating. Then an impedance is 6.5%, and this is the vector configuration, right? So transformer on the high side is wound a delta, and on the Y side is resistance grounded. Okay, so it comes in here, then it comes into the incomer bus, right? And this is the breaker for the incomer, right? Rated at 3200 amps. Okay, so this is bus A, bus B, and I explained the reason behind that is redundancy, right? Okay, and basically load demand and sharing of the load, right? Okay, so this is the rating of the bus, right? You have a nominal voltage of 2.4 kV as your operating voltage, and your continuous current is 3150 amps, and short circuit capability is 50 kiloamps at 1 second, and a three-phase, three-wire, 60 hertz copper bus, right? Okay, so this is the tiebreaker, Okay, and I explained the reason for the tiebreaker, right? Okay, we utilize the tiebreaker if we have to perform maintenance on one section of the bus. Okay, let's say we need to do maintenance on bus A or bus B, or if there's a fault on bus A or bus B, then that is when we need to continuously provide reliable power to those loads, right? So that is when we isolate that bus and basically close the tiebreaker based on basically an ATS scheme that basically detects the level of voltage, and basically there's a time delay utilizing certain protected relay, that is a sync check relay, ANSI device 25, and a timer, ANSI device 62. So based on that, they sense the loss of voltage on uh, one feed, and be able to close the tiebreaker to achieve that uh, scheme. Okay, so this is also another feed coming from another source, right? Okay, so this is the cable identification. So this shows that it's a three conductor, cable, right? That has the phase conductors as 185 mm squared, and the ground conductor as 95 m squared. Then it comes to this step down transformer that steps the voltage down from 13.8 kV to 4.16 kV or 2.4 kV. Then the rating of the transformer is 10 or 12.5 MVA, and 10 is the Onan rating. That is the natural convection rating, and the natural flow of air over the surface of the radiator without any fans. And the 12.5 MVA is the ONAF rating. That is a forced air. That is when basically the transformer, it's basically has stage cooling fans flowing, blowing air over the surface of the radiator to remove the heat, to be able to achieve the um, average temperature rise within the design specification. Okay, so this is the impedance of the transformer, and this is the vector configuration of the transformer DYN1. Okay, and this is shows that the white side is resistive grounded, and this is the capability of the resistance, right? Okay, so it can withstand 400 amps for 10 seconds, right? Okay, so basically your ground fault relaying will be set based on this, right? Okay, so they've determined that 400 amps is the amount of amperage that can flow within the transformer without causing any damage to the transformer. Okay, so this is the high side vector configuration. The high side, the transformer is bound in a delta configuration. Okay, so this is the incomer, right? Okay, so the incomer breaker, and this is the rating 3200 amps, and it comes in here. This is bus B, and basically bus B also has its cubicles that basically provides power to those loads. Okay, so now let's take a look at basically continuation from the previous slide. Okay, so now let's talk about 2.4 kV voltage level single line diagram. Okay, so I have a feed that is coming from the previous slide, right? So coming from a dedicated 13.8 kV switchgear lineup, it goes through a step down transformer, right? Okay, so you have a breaker here, then you have a switchgear 13.8 kV switchgear lineup, right? It goes from, then the transformer steps it down from 13.8 kV to 2.4 kV, right? Or it could be, three winding transformer, where you can have multiple of voltages, right? Okay, so then it comes, I've been able to step it down. Then I come in here, right? I have an incomer breaker, right? Okay, so I come in here. This is basically a motor control center, usually utilized to control motors, in the industrial facilities, right? Okay, so as you can see over here, we don't have breakers. We have basically fused disconnect switches and also contactors. Okay, so this is a contactor, right? And this is a fused disconnect switch. Then this is the bus rating. This is rated at 2.4 kV. Nominal voltage, and the continuous bus rating is 1200. The short circuit capability is symmetrical, right? For 1 second, they call it short time. symmetrical short circuit rating is 50 kiloamps RMS, and basically it's a three-phase, three-wire, 60 hertz, and a copper bus, right? Okay, so now let's talk about the disconnector switch. Okay, so the rating of the disconnector switch is 400 amps, and the fuse rating is 6R. Okay, so that is the rating for the fuse based on the horsepower and the full load current. So that's how the fuses are selected. Then this is the contactor, right? Okay, so in motor control centers, they utilize contactors instead of breakers, because contactors can withstand many opening, closing of the uh, tripping energization of the motor, compared to breakers. If you subject breakers to on and off, on and off, on and off, basically, you can end up, basically, degrading the operation of the breaker. So rather they utilize contactors in motor control centers to operate motors. So that is the reason why instead of breakers they utilize contactors, because contactors can withstand numerous switching, uh, you know, tens of thousands, compared to breakers. Okay, so and this is a fused disconnector switch. If basically you have to isolate the motor and basically perform testing or perform maintenance on it, then that basically helps you to disconnect, operate this disconnector switch. Okay, so the sizing of this disconnect switch, it's basically based on the horsepower rating of the motor. As you can see, this is a 350 horsepower motor, 400 horsepower motor, 350 horsepower motor, 200 horsepower motor, 200 horsepower motor, 300 horsepower motor, 1500 horsepower motor, 200 horsepower, and typical loads are for industrial facilities, and commercial facilities, and also generation facilities. Yes, so these are all contactors, that basically helps with the energization and de-energization of the motor, and a fused disconnector switch that helps with de-energization and performing inspection and performing maintenance. Right. Okay. So as you can see, they all have different ratings, right? The fuse, 12R, is all based on the horsepower, 800 horsepower, right? 12R, 200 horsepower, 4R, 200 horsepower, 4R, 350 horsepower, 4R, uh, 350, 350 horsepower is 6R, and 400 horsepower is 6R. 350 horsepower is 6R. Okay, so the sizing of all these fuses is based on the horsepower rating, and basically, based on the horsepower rating, you can get the full load amps of the motor, and based on the full load amps, and the withstand short circuit capability, the fuses are basically, selected. The size of the fuses are selected. Okay, so another single line diagram that shows 2.4 kV voltage level switchgear. Okay, so this is quite similar to what I explained. Basically, you have basically motors that are fed. Okay, so this is the feeder, right? That goes to the motor, and this is the size of the conductor. So the conductor, the cable identification is PC9790, right? And this cable has three phase conductors, right? 95 squared, and a ground conductor at this uh, basically section cross sectional area. Then this is another feed that goes to a 400 amps 400 horsepower motor, and this is basically the size of the phase conductor and the ground conductor. Then you have another feed that goes to a 350 horsepower motor, and this is the cable identification number, and the size of the cable is a three conductor 95 squared, and the ground conductor is 50 squared, right? And similarly, same thing, for these ones, and this is the size of the cable feed that goes to the motor, right? Okay, so similarly, like I indicated, these have contactors instead of breakers, right? Because contactors, you can operate it more, tens of thousands of times. But breaker, if you degrade, the breaker cannot withstand that amount of operations, right? So that is why they utilize contactors instead of breakers, and so you have a fused disconnector switch as well. Okay, so this is the rating of the bus, right? Okay, so now let's talk about 480 volts level, right? We've talked previous slides. We've talked about medium voltage level, 13.8 kV, 2.4 kV switchgear level. Now let's talk about the very low voltage side, right? Okay, so you can have another feed, right? Remember, I indicated that you can have 13.8 kV or 2.4 kV switchgear. Then it can either, you have a breaker in the switchgear that goes to a step down transformer, right? So step down transformer that will step the voltage down from 13.8 kV to 480 volts, right? Right. Then basically from there, you should be able to provide a feed. So that is what you're seeing over here. So this is the feed that comes in here. So it steps it down from 30.8 kV to 2.48 kV, right? This is the rating of the transformer, 2.5, 3.125. Okay, so the Onan rating without any cooling, right? Without any forcing cooling, right? No fans, is on at 2.5 MVA. But when it picks up additional load, then that is when the fans come on. So that's what they call ONAF. And this is the impedance of the transformer, and this is the vector configuration. It means that the high side of the transformer, 13.8 kV side, is wound in a delta configuration, and the low voltage side is wound in a Y solidly grounded, and the delta side is leading the low voltage side by 30 degrees based on the one. The one means 30 degrees. That's what it means. Okay, so this shows that the Y side, the low voltage side, is solidly solidly grounded. Right, that's what it means, and this is the delta. Similarly for this one, right? So basically, this is the incomer breaker, right? So the incomer breaker shows that the frame has a rating of 4,000 amps, and the trip plug has a rating of 4,000 amps. Okay, so these are solid state adjustable tripping, so they utilize the long time pickup, long time delay, short time pickup, short time delay, then instantaneous pickup, right? So these are basically the solid state adjustable trip devices. That's what these trip plugs mean. Okay, so the nominal voltage is 480 volts, and the nominal continuous current rating is 4,000 amps. The short circuit, you know 1 second short time rating, it's 85 kilo ohms symmetrical rating, and of course two buses, bus A and bus B, right? Okay, and this is the tiebreaker, so the stops that you see over here, the arrows, shows that it is redrawable for inspection testing, right? Okay, so these are all the feeds and the size of the breakers, right? Okay, so this shows that I have a feed here, and the breaker size is 1,000. So these are power breakers, okay? They call them power breakers. So 1,600 amp frame rating, and the trip plug rating is 1,600 amps. And similarly for this one, so the arrows shows that it is redrawable, right? It is redrawable, right? Similarly for this one, and this is the size of the cable feed from this motor control center. Okay, so this is another single line diagram of another 480 volts level motor control center. Okay, so or power switch, it could be either motor control center or power switch. Okay, so this is basically dedicated transformers, and this one has 1,000 kVA or 1 MVA transformer, and basically steps the voltage down from 13.8 kV to 480 volts. Why? And line to ground voltage of a 277 volts. Okay, so the 277 volts you see over here is 480 volts over root 3. So that is the line to ground voltage, or the phase to ground voltage. Okay, so The high voltage side is wound in the delta, and the low voltage side is wound in Y, solidly ground. So similarly for this one, okay. The impedance is 5.75 amps, okay. So as you can see over here, you can see that there are auxiliary cubicles, okay. So you will see that there's an auxiliary cubicle on all switch gears, right? Motor control centers, medium voltage switch gears, right? Okay, so that has instrumentation, right? So you see that this one has a watt hour meter. So what is the input to a watt hour meter? It's amperes and voltage, right? Because watt hour meter, needs it's a right watt hour, right? Okay, timing, and watts means current times voltage, right? Okay, so you need an input of amperage and you need an input of voltage. Okay, so you are able to synthesize the amperage from cities, dedicated cities that are in uh, the phase and bus. So probably this feeder over here, you have uh, cities that are basically, in that feeder that has been wrapped around that feeder. So this one we have three cities, right? Okay, one in each phase with a rating of 1,500 to 5, right? So the ratio is 300, right? Okay, so you have three of them, right? Then for the voltmeter, right, you have a PT that steps the voltage down from 480 volts to 120 volts, right? Okay, because you need to scale it down to a level of voltage that the watt hour meter can withstand. Okay, so the watt hour meter cannot withstand this high voltage, so you need to scale it. And also, the fusing is to protect these PTs from, over voltages, right? Okay, so this is the incomer breaker. On the size of the incomer breaker is 1600 amps. So this is a dedicated, or incomer or a main breaker. Depending on if oil and gas, mainly they call it incomer. Then this is the rating of the bus, right? And the tiebreaker, the rating of the other bus. Okay, so bus A, bus B. Redundancy is, and basically this is uh, the feeder that goes to motor, and another feeder, and this is the size of the breaker, and the size of the breaker, right? Okay, so you can even, scale the voltage down to a much lower voltage. You can even go from this level, go to another transformer. As you can see over here, right? There's a feed that goes to another transformer that steps the voltage down from 480 volts to 208 and 124. So that is when you need those voltages for a power panel. So that is when building facilities comes into play. You need a power panel at voltages of 208 or 120 volts. Commercial buildings. So that is when you need to step down these voltages, right? Okay, and similarly, you have another, feed from here. Redundancy is very important in design. Okay, with that, that comes to the end of my presentation, and thank you so much for your listening ears. And don't forget to select this like button in YouTube, and also don't forget to visit my YouTube channel. And there's tons of learning channels for you as a young engineer, as a developing engineer, as a disciplined engineer, and also, and even as an experienced engineer. You always need a refresher. And basically that can help you. Okay, refresh yourself on, a monthly basis or on a yearly basis. Okay, right. Thank you.